In physics, it's really hard to find things that move at a constant rate of motion, whether it is a ball flying through the air or bouncing or rolling along the ground, or whether it is a pendulum swinging back and forth, a ball rolling down a ramp. Usually you end up with things that speed up and slow down throughout the course of their motion. It's very difficult to find something that has a certain speed and stays at that speed the whole time. Now there are a couple examples and little tricks we can do to find things that do travel at a constant rate of motion. In other words, a constant speed or a constant velocity if you're dealing with the vector version that's going in a very specific direction. Okay? And one of those tricks that we can use is with a bubble moving through a viscous fluid. Okay? Or to be more general, a lot of things moving through a viscous fluid go at a pretty consistent rate. Okay, so for example, I have several viscous fluids in these tubes here. Viscous just means it's thick, it runs slowly, it has a resistance to flow. So this example here is ethylene glycol. This is one of the things they use in coolant and antifreeze in your car. It's not 100% ethylene glycol, but it's a mixture of ethylene glycol and water. Okay, now this stuff, and it's kind of like syrup. Okay, and you can see this bubble moving up, hopefully you can see it on the camera, through the liquid there. Now you might have also seen a couple pellets drop down here. We won't be using them for this lab, but they're there for other labs in case we want to look at motion aside from just the bubble itself. So they come again, the bubble is coming up from the bottom. Okay, so the rate of this bubble's position per time is pretty consistent, whether it's going a short distance or a long distance. Okay, so if we can track how long it takes for this bubble to get from one point to another, we can calculate its speed or its velocity. Okay, again, speed is just the scalar version of the rate of motion, how far something goes, distance per time, and velocity would be how far something goes, displacement versus a change in time. So in other words, going from point A to point B, and the direction it has to go in order to get from point A to point B. Okay? Now, keeping track of how fast this bubble is moving can be a little tricky because we'd be trying to measure position and time at the same time, which is tricky. Having a stopwatch in one hand and a marker in the other, and then having to turn the tube over and then start, and then I got to mark, and I got to keep an eye on the timer, and then I got to mark, and I got mark. It's tricky. Okay, so there are a couple things we can do to make this a little bit easier on ourselves. In order to slow the bubble down a little bit, instead of just going full force upright and allowing the bubble to rise through the liquid at its fullest speed, we're going to slow it down a little bit by tilting it kind of sideways. So it's going to be resting just a little bit inclined. So the bubble isn't just going fully straight up and down. This will also make it easier so we can rest it on something and then mark it while it's on the table. So that way we're not trying to hold it and mark it at the same time. Okay, so we can hold it like this. We'll elevate it on like a textbook and then make marks for where your bubble is. Okay, now you'll want to be consistent. Whether you are doing it at the front of the bubble or the back of the bubble is up to you, but mark it in the same spot on the bubble every time. If you're going for the middle of the bubble, mark it on the middle of the bubble every time and try and be consistent about it. Make sure the bubble's staying about the same size all the way throughout. I tend to like to do it at the back of the bubble, but that's just a preference thing. Again, as long as you're consistent, it should be good to go. Okay, now the easier way for us to do this is to do this on certain time intervals. Okay, so rather than seeing how long it takes to go certain distances, we're going to see how far it goes after certain times. And that's because we can make these marks at certain time intervals, like every 2 seconds or every 5 seconds, and then measure the marks later. Okay, it's a lot easier to measure distances or displacement after the fact than it is to measure times after the fact. Okay, you kind of miss your chance if the bubble's kind of already gone by and you haven't been timing it along the way. Okay, so about every 2 seconds or every 5 seconds, depending on how fast your bubble is going, we're going to be measuring where the bubble is every 2 or 5 seconds. And we'll be measuring those distances to figure that out. Now, our bubble should be moving at a pretty consistent, constant rate, which means even if the bubble is moving just a short distance or a long distance, the rate of motion should be the same. So if our bubble was, say, moving at about 5 centimeters per second, it should be moving at 5 centimeters per second, whether it's low or high in the tube, whether it's going from about here to here, or the whole distance of the tube. The rate of motion, the speed, or the the velocity, the vector version, should be basically the same, okay? Now, in reality, as human beings, we're going to have a little bit of error in how we make our marks, trying to get it right on the 2 seconds, and 4 seconds, and 6 seconds, or 5 seconds, and then 10 seconds, and 15 seconds. So we're going to see a little bit of variance. So to get a more accurate result, we'll be doing this for a couple data points along the tube and looking at the kind of speed or the velocity from one end to the other, okay, from one data point to the last data point. Right? So in order to do that, we're actually going to use graphs, which help us to collect that data and kind of summarize it a lot nicer than just trying to have a whole bunch of separate, distances and times. We could, say, okay, well, my bubble went this far in 2 seconds, and I take the distance divided by the time. And I could say, well, it went this far in 4 seconds, and take the distance divided by the time. And this is how far it went in 6 seconds, and distance divided by time. And I could average all those out. Or we can have a graph do most of the work for us. So let's talk about how that will happen. Set this back up here. Sure doesn't fall on me. Okay, so the speed of anything is just going to be how far it goes versus how long it takes to get there. In other words, if we take the distance, d, divided by the time, t, we should have the speed. Now on our graph, we're going to have distance on the y-axis, so how high up the bubble goes, with time on the x-axis, how long it takes for the bubble to get there. Okay? So if we are measuring out distance versus time like this, we should have data points for how far the bubble went after every so number of seconds. Okay? So maybe this is every 2 seconds. So every 2 seconds, the bubble goes up to this high. After another 2 seconds, it's this high. After another 2 seconds, it's this high. And it keeps going and going. Okay? Now, if we were to take this individually, d divided by t, you'd have to do this for every single point. And it would take forever and be so much calculator work. So here's what the kind of benefit of doing this with a graph is. I don't have to worry about any individual data points with this if I draw a line through all these points. Okay? So let me get a meter stick here. All right, so if we do this right, we should have about the same speed no matter whether you're looking early or late into your set of measurements. In other words, we should get a pretty straight line between our distances versus our times. Okay, we have a pretty constant, steady rate of motion, a pretty constant, steady speed. Now, this line has a slope. In other words, how steep or how flat it is. Okay, the steeper or flatter it is can tell us something. All right, that slope of the line is equal to the rise divided by the run. Or you might know that as the y divided by the x. Okay? Well, if the rise divided by the run is the slope, in this case the rise is distance and the run is time, the slope is the same as the speed on this graph. All right? Rise over run is distance over time. The slope is the speed. So if we can get the slope of this line, we know the speed of the bubble. Okay, all we need is one calculation for this slope of the line instead of all these 5 individual, this divided by this calculations for all of these. Okay, now what's even better is we can use programs like Excel or Google Sheets to plot these points out for us, to make the graph all nice and pretty for us, so we don't even have to worry about drawing it, and it can figure out the slope of the line for us. Okay, so the work that we'll have to put in to do this is very minimal. Most of it's going to be done by the program we're going to use. Okay, that's the power of the 21st century in technology, to be able to do calculations like this without having to do them by hand. Okay, so we're going to make the best use of that. Now, you could also do this in terms of displacement versus time, okay? So in that case, we're looking at velocity, so not just how far it goes, but in a certain direction. So in this case, our bubbles are always going to be kind of moving upwards at an angle. So if you wanted, you could say we're calculating the velocity of the bubble from, like, say, this to point, this point, or this point, or this point, depending on which way you have your tube, okay? And the equation looks a little bit different, but it's basically the same. It's how far your thing goes and how much time it takes to get there. All right. Displacement we usually show by a change in x or a change in y. And since we're looking at how high up the bubble goes, we're going to use y. That's typically what you use for your vertical axis, your up and down axis. So a change in y would just be how high or low something is going from one point to another. Okay. Our change in time would be going from left to right. This little triangle is just called the letter delta. It's a Greek letter, and it means the change in something, like the change in time or the change in vertical position, like change in y. Okay? Now, just like before with the speed, the slope of this line can tell us a lot. It is basically going to tell us how much ground we cover in a certain amount of time. Whether you're looking at that just between these 2 points, how much this way for how much this way, or if you do for the whole thing, how much this way for how much this way. Okay, ooh, that was close. So, your rise over your run is going to be the same as your displacement over your time, okay? Or your delta y over your delta t. However you want to write it, it's basically going to be the same thing. It's how fast your thing is moving, okay? How far it covers versus how long it takes to cover that distance, okay? So whether you want to call it speed or velocity, whether you include the direction or not, whether it's a scalar or a vector, if you are looking at the rate of motion, the slope of the line is going to make it so much easier to calculate how much distance we cover versus how long it takes for that to happen. No individual calculation is necessary. Okay? So we're going to be doing this, graphing out data points like this and having Google Sheets or Excel do the rest for us, okay, with a couple different examples of oils. Depending on how thick the oil is, the bubble might move faster or slower. So some of these, it might be best to do with data points every 5 seconds, like this guy, which is moving pretty slowly. Okay. Or others might move pretty quickly, so we might take data points every 2 seconds. Okay. Now in the end, we're still going to take distance divided by time, so it's going to be centimeters per second in this case. We're going to measure centimeters of distance or displacement divided by seconds of time. So whether you pick every 2 seconds or every 5 seconds, whether you pick every 2 seconds or every 5 seconds or every 10 seconds or every 1 second, shouldn't change really a whole lot about what's going on. Okay? As long as you can keep consistent data over time, you should be good to go. Now I'm going to clean this up and make sure I didn't break anything. In order to figure out the speed of the bubble that travels through this tube, all we have to do is keep time measurements and position measurements of this bubble. What's going to be easiest is to do this at very specific times and mark where the bubble is at those times instead of trying to measure the time at certain positions. So we're going to make a mark about every 2 seconds because that works out pretty well for the size of this tube and how fast the bubble is going. And then we'll be able to graph those data points once we have those collected. So for now, all we have to do is make the marks every time the bubble kind of moves for 2 seconds, and we'll be able to measure kind of how far the bubble has made it each of those 2 seconds. Okay. So I'm going to flip this around here. So right now the bubble is up at the top. And when we lower this end down, this will be the top, and the bubble's going to start going this direction. So, here we go. 2, 4, 6, 8, All right about there. Now, since we picked these points, there's not really a reason I have to start at the end of the tube here, even though the bubble started down here. Since I took my first measurement here, then I can say that's where I start my meter stick. So your 0 seconds position is going to be 0 centimeters. From there, we're going to be counting up from there. So you'll always have a data point at 0 seconds and 0 centimeters and work up from there. So we can take our measurements at each of these, 0 seconds, 2 seconds, 4 seconds, 6 seconds, 8 seconds, and then be able to graph those out using Google Sheets. Okay, now for our ethylene glycol, we can measure out our distances for every 2 seconds we did on this one. So this being our kind of starting 0 second line is going to be our 0 centimeter line. Our next one comes out to be about, that's 10, so 19 point, maybe about 0.1. So I'm going to say 19.1 centimeters. Let's go to the next one. This next one's about 36, pretty much right on the dot. 36.0, or just 36. Next one's about 53.1. This one's about 71 point, this is 5.6.7, about 0.8. So 71.8. Oop. And then we hit the end of the tube. So there's our data points. So at 0 seconds, we hit 0 centimeters, then 19.1, then 36, then 53.1, then 71.8. This is our red mystery oil. So we're gonna turn this one around. We're gonna do this also about 2 seconds. All right, so because this bubble tends to move a little bit faster, so here we go. 2, 4, 6, 8, 10, 12, and then we hit the end. So in that case, we didn't get to have a whole 20 seconds in there, but that's okay. We have enough data points to make a trend to be able to figure out the rate of motion from here to here. So just because we decide ahead of time, oh, we should do it for 20 seconds, doesn't mean we have to hold to that, as long as we have enough data points here. If you really wanted more data points, you could do kind of shorter limits of time. So you could do every 1 second or every half a second if you were so inclined. Okay, this is our mystery red oil that we recorded marks at every 2 seconds. So we have, this is our 0 second mark, so this is also our 0 centimeter mark. This is where we're starting our measurement. Then our 2 second mark would be about 6.5, maybe 0.6. 6.6. You just gotta do your best when you're eyeballing it. Ooh, that's a terrible 6. It's just getting worse. I'm gonna move on. That's supposed to be 6.6. All right, this is 10.35, about, so 13.6. This one's about 20.5. This looks to be about 27.2. This one's about 33.4. This one's about 41. Ooh, pretty much on the dot. Let's do that. Let's just do 41.0. All right. So we went from about 0 to 6.6 to 13.6 to about 20.5 to 27.2 to 33.4 to 41 every 2 seconds. All right, this is our mystery blue oil. Turn this around. We're going to do this every 2 seconds for about 20 seconds. So here we go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right, and notice we didn't make it to the end of the tube all the way on that one. That's okay. Like I said, we only need as many data points as it takes to get a good trend from here to here. Okay, this is our mystery blue oil. This is our starting line, so our 0 centimeter mark here. We started our timer at 0 seconds. All right, so this one's going to be about 2.567, about 2.8. This one's pretty much right on 5.0. This one's at about 7.6. This one's pretty much smack dab on 10. At 12.5 or 12.6. Let's go with 12. Let's go with 12.6. And we're at about 15. Let's do 15.1. That's about, I'm going to say 17.9. Say that's about 20.567, 8. Let's do 20.8. Ooh, there we go. 20.8. This is about 23.4. And our last one's about 25 point. I'm gonna say 25.8. 25.9. All right. So for every 2 seconds, we went from 0 centimeters up to 2.8, 5, 7.6, 10, 12.6, 5.1, 17.9, 20.8, 23.4, and then 25.9. All right, this is our green oil, mystery oil. We're gonna be doing this every 5 seconds for about 40 seconds. So here we go, bringing the end down. 5, 10, 15, 20, 25, 30, 35, 40. All right, and then we just measure this out. Now for our green mystery oil, it's going to be our 0 centimeter mark. And this is going to be about 4.1. This is going to be about 8.4. And I should say, keep in mind that for the green mystery oil, we moved up to about 5 seconds for each, about 5 seconds for each mark. So from 0 centimeters to 4.1 centimeters, that was 5 seconds. And another 5 seconds passed to get from 4.1 to 8.4. All right, our next point is going to be about 12.4. Then we're at about 16.5. And then about 20.3-ish. 1, 2, I want to say 20.2. Okay, here's about 26.1. Yeah, 26.1. It's going to be about 31.5. That's about 36.2. 7. And that's the end of the tube. So there's our mark. So every 5 seconds we made a mark. We wound up at 0, 4.1, 8.4, 12.4, 16.5, 20.2, 26.1, 31.5, 36.7 centimeters. This is the SAE 20W50 motor oil. Turn this around. So the bubble end is going to be coming towards here. Here we go. Five, 10, 15, 20, 25, 30, 35, 40. All right, like I said, we can measure that out from our first point, which is our 0 second mark, all the way up to the 40 second mark. All right, this is for our SAE 20W50 motor oil. So back down to the beginning. So at 0 seconds, we had this mark right here. So this is going to be our 0 centimeter mark. All right. The next mark is about 5, 6, 7, about 2 point, I'm going to say 2.8. Then about 5.5. And about 8.1. And this is about 11.1. Let's see, this would be about 14.0. This one's about 17.0. This one's about 20.0. This one's about 23.1. And then that's it. Let's check those out there. So, yeah, so once it gets on a roll, you go from every 5 seconds, we take a mark. So after 5 seconds, we go from 0 to 2.8 centimeters. After another 5 seconds, it gets to 5.5. After another 5 seconds, it gets to 8.1, then 11.1, 14.0, 17.0, 20.0, and then 23.1. All right, this one's Glycerol. It's used as a thickening agent for a lot of like hand soaps, some stuff in foods. So I turn this around, so our bubbles at the top here, and lower this down, and we'll do our data points about every 5 seconds up to 40 seconds on this one too. Five, 10, 15, 20, 25, 30, 35, 40. Now, even just where your marks land can tell you something a little bit about the velocity. If we're doing this in the same amount of time, like this took 40 seconds from here to here, if another bubble takes, here to here distance-wise in 40 seconds, you can tell that it has to be moving at a faster rate to get that much farther in the same amount of time.
Okay, this is our glycerol, where we took marks every 5 seconds. So this is our 0 second mark, 0 centimeters. Then we have one at about 2.567, so 2.7 centimeters after 5 seconds. We hit 10 seconds, we're up to about 5.567-ish. See, and we're up to about 8.5. Then to about 12.0 on the dot. And we're up to about 14.8. And about 18.1. That's about 21.4. And that's about 25.0. And that's the last mark. So every 5 seconds we make a mark. So we went from 0 centimeters to 2.7 to 5.7 to 8.5 to 12.0 to 14.8 to 18.1 to 21.4 to 25.0.
All right. This tube has SAE 10W40 motor oil in it. All right. So we're going to measure the speed of the bubble in this one too. So let's flip this around. Let the bubble start at the top. All right, and we'll just keep marking data points for however long it takes for the bubble to get to the other end. Once you hit 20 seconds, that's plenty of data points, so we can stop there. Here we go. Wait for the bubble to come out.
Two, 4, 6, 8, 10, 12, 14, 16, 18, 20.
So just from that short length, we've already got the basically 10 data points that we need. And if the bubble's moving at a pretty consistent rate, it shouldn't matter whether we're measuring them here or from end to end, as long as we've got them at kind of good intervals in between here.
Okay, this is for our SAE 10W40 motor oil. This was our 0 centimeter mark at 0 seconds. Then after 5 seconds passed, we were up to 5.567, about 5.7 centimeters. And we got up to about 10 point, oh no, that's sorry, it's about 11.2. So that's at the 10-second mark. So at the 15-second mark, we're at about 17.123, yeah, at about 17.3. And we're at about 23.5. And we're at about 31.5. And about 37.1. About 43. Yeah, about 43.5. And about 50.5. Okay, so we went from 0 to 5.7 to 11.2 to 17.3 to 23.5 to 31.5 to 37.1 to 43.5 to 50.5.